In this problem, we want to determine the Thevenin equivalent circuit seen by the 1 amp source. That means what we want to do is take the 1 amp source out of this circuit at its terminals, say A and B, determine the voltage current relationship that the rest of the circuit is applying across those terminals. That'll be our Thevenin equivalent circuit. So taking the 1 amp source out, the circuit that we're actually working with is this 4 ohm resistor, an 8 volt source. The terminals that we want the voltage current relationship across, so A and B, and then this 4 ohm resistor. So what we're going to do is have an open circuit voltage, VOC, and a Thevenin resistance, RTH. And at these terminals A and B here, anything that we connect at these terminals will see the same thing that we connect at these terminals. So we need to find two things, the open circuit voltage and the Thevenin resistance. Those are two separate problems. I think I'll do the Thevenin resistance first. So RTH. I kill the sources, so I have this 4 ohm resistor. A voltage source, when I kill it, becomes a short circuit. Here are my terminals, A and B, and another 4 ohm resistor. Now keep in mind that these are drawn like it's an open circuit, but what we're actually doing is finding a relationship between voltage and current here. So if I put a little voltage across here, I'll get some current through there. So if it was an actual open circuit, that current would be 0 by definition. It's not. We're looking for a voltage current relationship, which is just a Thevenin equivalent resistance. So we have RTH. This 4 ohm resistor is in parallel with this 4 ohm resistor, so it's 4 ohms times 4 ohms over 4 ohms plus 4 ohms. So the Thevenin resistance RTH is 2 ohms. Now, as a completely separate problem, we can find VOC. Now, we redo our circuit. From here, I have a 4 ohm resistor. Put your sources back in, so 4 ohms plus minus 8 volts. Terminals A and B are here, and this is also a 4 ohm resistor. Now in this drawing, terminals AB actually do form an open circuit, so there's no current through here. I is equal to 0 by definition. Now we want to find VAB, which is going to be my open circuit voltage. I can find that by any approach that I want. So this circuit is simply a voltage divider. This 4 ohm resistor is in series with this 4 ohm resistor since there's no current here. So VOC is the total voltage, 8 volts, times 4 ohms, which is the voltage across this guy, which is VOC, over 4 ohms plus 4 ohms. So this becomes 4 volts. So now our Thevenin, let me get rid of this up here and actually put the numbers into it. So our Thevenin circuit is a 4 volt source in series with our RTH, 2 ohms. And these are terminals A and B. Now, the next thing I want to do is use the result to determine the voltage V1 in this original circuit here, the voltage across the 1 amp source. To do that, I put the 1 amp source back into the Thevenin circuit. So in this circuit here, I'm going to have a 1 amp source, and the voltage across that source is V1. So if this is 1 amp, this voltage here is, say, Vx, which is going to be 1 amp times 2 ohms. So V1 is equal to this voltage, V sub x, plus 4 volts, which is 2 ohms times 1 amp plus 4 volts. This is just V sub x, so this is 6 volts, and V1 here is 6 volts. Now, as I said, the way I determine the open circuit voltage is not unique. You can use any of your analysis methods to find that. Make a little room here. So it's still the same circuit that I used here. That doesn't change. I always deal with this circuit. It's a 4 ohm resistor, an 8 volt source. The terminals that I'm looking for the Thevenin circuit across become an open circuit, so this is VOC. And keep in mind that in this case that current has to be 0, and then 4 ohms here. Now in this case I did circuit reduction. Which let me do a voltage divider. I could just as easily do nodal analysis. If I make this my reference node, 0 volts, there's only one independent node. It's up here. Call it V sub A. Here's a dependent voltage, which is 8 volts above 0, so there's a dependent voltage. And doing KCL at node A, I have V sub A minus 8 volts over 4 ohms, which is this current in this direction, plus V sub A minus 0 volts over 4 ohms. That's equal to 0 because remember this current here is 0. Multiplying through by 4, I get 2. VA is equal to 8 volts, and VA is 4 volts. VA is exactly the same as VOC. So luckily, we got the same answer regardless of which analysis approach we used.